All right, section, what are we on? 14.2 is double integrals. And volume. And let's actually switch to black here. Okay, so remember in Calc 1, when you were learning about integrals, we looked at the integral as measuring the area under the curve f of x. And we did that, say we wanted to find the area between 2 points A and B. Well, we broke the interval A to B into a partition. And so on, whoops, all the way through xn. And we created, whoops, bars of some height between each interval in our partition. And we calculated the areas of those bars. And as our partition became larger, so we had more points in our partition, that area became, the sum of the areas of those bars became closer and closer to the actual area under the curve. So say we calculated the area as approximately the sum from I equals 1 to n of f of, I'm going to put xi star times delta x, where delta x is the width of your partition, right? The width between points in your partition. Xi star was just a point that you chose, say, to determine your height. So this would be x2 star comma f of x2 star. All right, and so if I wanted to know the area under this curve, we took a limit, right? So the limit as n approaches infinity of the sum I equals 1 to n of f of x I star delta x. And this is our definite integral from a to b of f of x dx. Okay, so we want to model that now in the 3D case. Okay, so now in Calc 3, my domain is no longer just on the x-axis, right? My domain is some region, oops, that's not z, some region in the xy plane. Here, I'm going to just pretend that my domain is rectangular. So say this is my region R. And we're going to use the same idea as we did in Calc 1, except now instead of partitioning just the x-axis, I need to partition both along the x-axis and the y-axis. And what I'm going to get is a grid, something that looks like a grid. So say I cut this up into pieces and cut the y-axis into pieces, and then I'm going to draw the grid that I get here. Okay, and we're going to call this a mesh. And so I could pick a point inside each of these rectangular pieces. We'll call this xi star yj star. And that's going to be the point over which I want to evaluate my surface. So say my surface looks something like this, coming, oops, above that region. Let's see if we can make this even lighter. So I've got some surface here over which I'm trying to integrate. And so now instead of drawing bars, I'm going to, let's use black, draw these 3D prisms coming up from each. So maybe here's where f of xi yj is. Okay, so that's not a great picture, but hopefully you get the idea. And so I'm going to create a bunch of these prisms and calculate their volume. And if I add them up, just like we did in Calc 1, that should estimate the volume under this surface. Okay, and so that's the idea when we're looking at double integrals. So let me be a little more formal here. So the double integral, let's suppose f is defined on a closed and bounded region R, closed and bounded, in the xy plane. Then the double integral over R of f of xy dA, so the area here of these rectangles is changing. Okay, so is defined to be the limit as the size of delta goes to 0 of this double sum. Say j equals 1 to m, I equals 1 to n, of now f of xi star yj star delta aij. Okay, now your book doesn't bother considering the fact that, you know, your mesh might use a different number of intervals for the y-axis than it does for the x-axis. So your book just more succinctly writes this as the limit as the magnitude of delta goes to 0 of just the sum I equals 1 to n of f of xi yi delta ai. So here we're assuming that, whoops, that's an I, that the mesh we've chosen is size n in both directions, and we're just going to use xi, yi as our point that we're evaluating the function at. All right, so this is the definition of the double integral provided the limit exists. And if it does, we say f is integrable over R. Okay, so we're just taking what we did in Calc 1 and building it up a level in up a dimension in Calc 3. Okay, so what does this double integral give us? It gives us volume. So let's write that down. So if f is integrable over a plane region R, and f of xy is positive or non-negative for any xy in the region R, then the volume of the solid region that lies above R and below F is exactly the double integral over R of f of xy dA. Okay, so let's look at an example. I want to consider the region in the first octant bounded by the 3 coordinate planes and the plane z equals 8 minus 4x minus 2y. Okay, so the first thing you want to do is try to get a picture of what's happening. Now you could sketch this in GeoGebra, or you could, with planes, it's not so bad to just sketch it yourself. Okay, so I've got x, y, z. Remember, with planes, when we draw a sketch of the plane, we look at where it crosses each of the axes. And in this case, that's really all we care about because we're just looking in the first quadrant. Okay, so if I let x and y both be 0, I get that z is 8. So it crosses at z equals 8. When y and z are both 0, I'm going to get 8 minus 4x equals 0, so x must be 2. And when x and z are both 0, I'm going to get 8 minus 2y equals 0, so I need y to be 4. Okay, I'm not being super careful to make sure that my scale is the same on each axis, but this is what we have. Okay, so inside the blue, maybe let's try highlighting it again. Here's what my plane looks like in the first quadrant. All right, so how could we find the volume of this region? Oops. So we're going to look at 2 ways of doing that. So in the first way, I want to look at the triangle. So let's say I'm at some point x here, and I want to look at the triangle that I get here inside, underneath that region. Okay. So this is some point x. So what's the area of the triangle drawn? Well, in general, area of a triangle is 1/2 base times height. So let's see if we can figure out the base and the height of this triangle. I'm going to zoom in a little bit. Well, to get the base, I'm looking at going from x here, well, really from y equals 0 to this line. So what is the equation for this line? Well, it's the part of the plane that lies in the xy plane, right? So the part of the original plane that lies in the xy plane. So we just need to set z equal to 0. So this is the equation. 0 equals 8 minus 4x minus 2y. And so if I rearrange this, this is y equals, let's see, negative 2x plus 4. You agree with that? So I move the 2y over and then divide through by 2. All right, so the base goes from y equals 0 to y equals negative 2x plus 4. So the base has width negative 2x plus 4. Okay, now I want to do the same sort of thing for the height. The height is going this way, so it's going from z equals 0 up to this point here. And again, this point lies on the plane, the part of the plane that intersects the xz plane. So I'm going to set y equals 0. So this is z equals 8 minus 4x. And so the height of that triangle is 8 minus 4x. Okay, now I know you can FOIL this out on your own, so I'm just going to jump to the answer for the sake of time. You're going to get 4x squared minus 16x plus 16. Now that's the area just of this triangle that we've drawn. So if I wanted the volume of this whole region, imagine, I wish I had a slider, imagine that I just took that triangle. Actually, let me use the laser. Imagine I took this triangle and just added up the areas of all the triangles that are inside here. Well, when we add things up, what do? We integrate, right? So we're just sliding that triangle along the x-axis and integrating it. And in fact, let's slide it this way, right? Starting when x equals 0 and going until x equals 2. So the volume is the integral from 0 to 2 of the area, right? So 4x squared minus 16x plus 16 dx. All right, now this is a calculus problem, Calc 1 problem, so I'm just, again, going to jump to the answer. You're going to get 32 thirds, which is about 10.67. Let's say units cubed. Okay, so that's our first approach. Our second approach is to use integration to find that area of the triangle. So note, let's call this 2. We could have used integration to find a of x. Let's call this a of x. All right, so think about that triangle again. I'm going to draw it with a little more room here. It starts at y equals 0 and goes to y equals negative 2x plus 4. And this is along the plane z equals 8 minus 4x minus 2y. And this is going to be horizontally simple. Sorry, vertically simple. Okay, so what am I going to do? I'm going to integrate the height, 8 minus 4x minus 2y, with respect to y now, from 0 to negative 2x plus 4. And that's going to give me the area of that triangle. All right, so if I integrate with respect to y, I'm going to get 8y minus 4xy minus y squared, evaluated from 0 to negative 2x plus 4. If you plug in for y and simplify, I'm going to skip a few steps again just for sake of time. You can pause the video and work it out yourself to make sure you agree. I'm going to get 4x squared minus 16x plus 16. Now notice, that's the same thing I got up here, which is good, right? That's the area of that triangle. And again, if I want to take the volume, I need to integrate now over x. And so the volume is the integral from 0 to 2 dx of this integral, right? So of the integral from 0 to negative 2x plus 4, 8 minus 4x minus 2y. Oops, dy. Let me make some space here. Okay. So I can represent the volume with a double integral. And that is exactly Fubini's theorem. I am actually going to jump to the book and show you Fubini's theorem rather than writing it out. So let me switch to the book real fast. Oh, and actually, we got to do it. I'll just show you everything I have open. Here we go. Oh, no. Okay, it's logged me out. Let's just write it down. Fubini's theorem. Suppose F is continuous on a plane region R. Then 1, if F is defined by A less than or equal to X less than or equal to B, and Y is bounded by functions G1 of X and G2 of X, where G1 and G2 are continuous on AB, then the double integral over R of f of xy dA can be written as an iterated integral from A to B of the integral from G1 of X to G2 of X of f of xy dy dx. Okay, so we can use our iterated integrals from the last section to evaluate double integrals in this section. All right, similarly, if your region is defined with real valued bounds on y, and x is bound by h1 of y and h2 of y, where again h1, h2 continuous on now CD, then again the double integral over R of f of xy dA is the integral from C to D of the integral from h1 of y to h2 of y f of xy dx dy. Okay, so looking back at our example, so let me actually flip the page. I'm going to look back at this picture. My region R of integration is down here in the xy plane. So it's this triangle down here in the xy plane, which is the triangle that goes up to 4 on the y-axis and hits 2 on the x-axis. All right, and using methods from the last section, we can write the iterated integral over this region. Let's go with a vertically simple. Let me cut this and paste it on the next slide. Okay, so there's our region. This is, whoops, delta x. So y, my bounds on y are from 0 to this line, which is the line y equals negative 2x plus 4. And my bounds on x are x runs from 0 to 2, right? Okay, so Fubini's theorem tells us that the volume of the region in the first octant, bounded by the planes and the plane 8 minus, what did we have? 8 minus 4x minus 2y is the integral of 8 minus, double integral, 8 minus, my goodness, 4x minus 2y. We're going to do y runs from 0 to negative 2x plus 4, so dy here. And then x runs from 0 to 2, so dx there. All right, which is exactly what we found on the last slide. All right, I'm going to pause here and let you try a problem in WebAssign, and then we'll come back and talk some more.